Okay. Good morning, good afternoon, good evening. Anywhere we are. It's a pleasure to be here today at the third global webinar on artificial intelligence and data science. Um, but just before I proceed, just want to confirm if my video is showing. I put on my video, but I just don't know what's going on. My system is just a bit slow this afternoon. So,
Yeah, we are able to
hello.
see the screen.
Okay. Okay, so my name is Lanre Shittu, and I'm excited to share insights on a topic that is shaping the future of the construction industry, the future of concrete testing, machine learning approach. Just bear with me. Okay, so so this is actually overview of what I'll be discussing during this presentation. And my next slide. Okay, so concrete is actually the most essential and commonly utilized material in civil engineering, such as construction of buildings, bridges, tunnels, dams, and other related civil structures. Concrete actually has numerous properties like tensile strength, compressive strength, durability, and so on. However, the traditional way of actually evaluating these properties are often time consuming, labor intensive, costly. But with the involvement of AI, we can actually analyze and improve the testing of concrete strength faster, more accurately, and at a lower cost. So, next slide. Okay, just bear with me, please. Okay, so the traditional way of testing concrete actually refers to established method used to assess concrete properties, and most of the times, this method actually involve destructive or semi-destructive process that actually lead to wastage of materials and errors in measurement at times, time consuming and tedious and costly also. So there are different properties of concrete assessed traditionally, but the ones considered in this study are actually compressive strength of concrete, concrete durability, and image processing in concrete. So starting from the compressive strength assessment, so this actually rely on the concrete crushing tests, which are actually destructive, time consuming, tedious, and costly. Then also talking about the concrete durability, this actually evaluate the long-term performance and resistance of concrete to environmental and mechanical stresses, ensuring structural integrity and longevity. This method as well are slow, costly as well, and tedious to carry out. And the last one, which is image processing in concrete. So this process is to actually detect cracks, void, and reinforcement issues in concrete, which is prone to errors. Also tedious and time consuming. The next slide. Okay, sorry if these images look horrible. So this is like 10 years ago. I don't know if this is showing over there. Hello?
Yeah, it's not visible.
Hello? Can
Hello.
anyone hear me? Oh, yes. So I'm actually showing some images. So I don't know if you can see those images from there. Hello?
Yeah, hello. Am I audible?
Yes. So I said, yes. So I said I'm sharing some images. So just want to confirm if they are visible from there.
Yeah, it's visible now.
All right. Okay. So that's fine. So these images look horrible. Sorry about that, but this was around 10 years ago. when I was working as a civil engineer on a construction site back in my country, Nigeria. So, as we know, construction of buildings are actually done in stages to completion. And for instance, we start from the foundation, from there to ground floor slab, which is what we know as the German floor, and so on to completion stage. And at every stage of this construction, we actually carry out tests to actually ascertain the structural integrity of these structural elements. So here in these images are some of the samples of structural elements to be tested in the laboratory. So I'm actually here we have samples, these are just some of the samples we actually take to lab to test. So we can see how many they are, and each of them actually weighs up to 50 kg. They're actually very heavy. So um, let's say we want to test the compressive strength of columns, which is what we know as pillars. We actually start from sample preparation by mixing cement, water, sand, and stones together. And these samples are actually casted into different shapes, which could be in cubes or cylinders. And after preparation of the samples, then we actually subject them under what we call curing, that is, keeping them in a big storage tank under water, moisture, and temperature, just to make sure that they achieve their strength, which could take up to 7, 14, 21 to 28 days. So, and after that period, we actually assume that the concrete samples have actually acquired the strength, and we then take them to the laboratory to actually test them. Um, so when we take these samples to the laboratory, as we can see here, so we actually put them under this machine here to actually crush them. So this machine actually applies pressure to actually crush those samples. And when we are done, we actually record the measurements. So just for us to get the compressive strength of a single color, right? We actually perform up to like 3 samples, and we actually find the average of those results, which we actually get. So this also another machine we actually use to actually crush those samples, you know, and um, achieving just a compressive strength, right? It's just like I said, it actually involves preparing and crushing up to 3 samples, and we find the average of all of these. And so imagine if we want to repeat this process for like 200 columns, that is 200 pillars, and the high-rise building, for instance, can have thousands of these pillars in them, and these pillars are just one element in the building, because we still have other structural elements, such as the beams and the slabs. So just imagine that we have to perform all of these tests for each of these elements. So it's really a lot of work to be done. And these machines, which we are seeing here, just the one here, and this small one here, and the ones we have here, they're actually very expensive to actually set up, and only few laboratories can actually afford these machines, to the extent that engineers actually often travel several miles just to complete this process of testing in the laboratories. So we can see that the traditional method is destructive, as it requires physical samples to be crushed doing testing, and time consuming, costly, tedious, and prone to errors as well. Next slide. Okay, so aside the compressive testing of concrete, so the other testing we have is actually durability testing of concrete. This actually involves sample preparation, which I've discussed earlier on, then curing, which I've also discussed earlier on, then testing. But in this case, under durability testing of concrete, it involves more than one test. The previous one was just a comprehensive testing, but this one has a chloride penetration test. There's a carbonation depth, there's a freeze-thaw resistance, and there's a abrasion resistance. So this process is tedious as well for durability testing of concrete. It also comes with human error, time consuming as well, and and just like I said, because there are several steps that are involved. It makes this process tedious and it raises safety concerns. And next slide. These pictures, I don't know if you can see these pictures as well. The pictures are taking time to load. I don't know why. Um, Sorry, are those pictures showing from your hand, please? Just to confirm before I proceed. Kiran?
It's not visible. It's not visible.
Okay, I think it's because it's still loading. Just my system is just too slow.
Yeah, got it.
Um, Sorry about that. My system is just too slow. I just don't know what's going on. So this is not how it is. It's because it's actually slow in loading.
Yeah, it's
So
perfect now.
okay, yeah. So sorry about that. So these pictures here show myself with some fellow engineers some years back, trying to perform various tasks related to concrete testing for durability and structural assessments. So sorry if these pictures look horrible as well. So they're actually taken from horrible camera. So just bear with me, please. So this actually involved testing with a rebound hammer. So what I'm holding here is actually a rebound hammer. I don't know if you can see what I'm doing. So this is a rebound hammer, and this is a drilling machine here. So what we are trying to do is to use this drilling machine to actually drill out a sample of this concrete slab here. Then also we have this person climbing on a ladder, trying to test a portion of the building, and here is me here as well trying to test this portion of this building, and all of this setup, this equipment setup, as small as they are or as they look, they're actually very expensive. And during the process, there's high tendency for errors to occur during the measurements. And as we can see, this part of the building were actually chiseled out, just before we're able to test this part of the building. So there are some destruction in place as well, and it raises safety concern as this person on this ladder, there's risk of falling for that's for this person climbing on the ladder. So when we look at all of these things, so we can see that it's really a tedious task, so which actually gives reason for a better ways of getting all of these things done. So next slide. Uh, uh, okay, I think it's up now.
Yeah, it's okay.
Okay. I'm so sorry. Is my system is extremely slow from here. So sorry about that. So from all of this, there has been a great need for faster, cheaper, less stressful, more accurate, and sustainable concrete testing method in the construction industry. And with the advancement of AI, concrete testing process has actually been optimized, addressing most of the shortcomings from the traditional ways. And several machine learning techniques, including gradient boosting regression, extreme gradient boosting, support vector machines, artificial neural networks, and lots more have demonstrated over the years superior performance in predicting concrete mechanical properties. So let me next this slide from here. This is just too slow. So sorry about that.
Yeah, Mr. Lanre, can I share from my end?
Okay, so let me just send you what I have here. Sorry, just bear with me, please. Just bear with me. Because what I have here is not what you have there. Just bear with me while I share what I have here, please. Just bear with me, please.
Okay.
Just bear with me. Or do I just go ahead with what I have on the screen now?
Yeah, it's okay. It's visible.
Okay. So sorry, my system is just acting this way. So sorry, please. Okay, so starting from predicting compressive strength of concrete with machine learning approach, over the years, several researchers have actually utilized this technology to determine strength of concrete, and from starting from Gunimat et al. So they actually performed an experiment where they predicted the compressive concrete strength with random forest regression and k-nearest neighbor. So they found that random forest regression actually predicted best with correlation coefficient of 0.973, and that's high enough. And secondly, an experiment performed by Wu et al. So they predicted strength of concrete as well, but this time around using the logistic regression, multiple linear regression, and k-nearest neighbor, support vector machine, decision tree, and random forest regression, and also backpropagation neural network. And in this case, it was observed that k-nearest neighbor actually predicted best with correlation coefficient of 0.998, and followed by the third experiment by Wang et al. So in this case, they actually predicted the compressive strength of concrete containing ground granulated blast furnace slag um, by using random forest regression as well, extreme gradient boosting, support vector machine. And in this case, they observed that support vector machine actually predicted best with R square equals to 0.86. And likewise, an experiment performed by Gregory et al. They also assess the concrete strength with Gaussian process regression and support vector machine. And from here, we can see that support vector machine performed better than Gaussian process regression. And lastly, an experiment performed by Sharma et al. In 2022, they also predicted compressive strength of concrete with some machine learning models using random forest regression 3, genetic programming support vector machine, adaptive neural fuzzy inference system, and artificial neural network to predict the strength of concrete. And they actually found that ANN, which is artificial neural network, actually predicted best this time around with R square equals to 0.914. So these are all of the past researches, using the machine learning approach to determine compressive strength of concrete. So I'm trying to next my slide from here. I hope this is okay. So I have another table here before me. I don't know if that is showing over there.
Yeah, it
So
was
I've just, sorry, is that what?
Yeah, it's visible.
All right, thank you so much. So this table actually, it was from a research conducted by me. So in this research, I actually utilized random forest regression, support vector machine, and a k-nearest neighbor to predict the compressive strength of admixture mixed concrete on a 1030 data set. So this table illustrates the performance of the three machine learning models evaluated, employing correlation coefficients and the root mean squared error and the mean absolute error. As we can see, it was observed that random forest, which is this. So this random forest actually demonstrated the best performance, achieving the highest correlation coefficient of 0.99 against zero 0.8 for k-nearest neighbor and against 0.57 from support vector machine. And also this random forest had the lowest mean absolute error of 1.30 against 5.61 for k-nearest neighbor and against 8.15 for support vector machine. And also random forest has the lowest value for root mean squared error, which is a 1.96 against 7.54 for k-nearest neighbor and against 11.10 for 11.1 for support vector machine. So this research that was conducted by me simply means that random forest was a good machine learning model to actually use to predict compressive strength of admixture mixed concrete. So next. So I'll just next the slide.
Yeah, it's visible.
Okay, it's visible. All right, thank you. So, assessing the durability of concrete is actually a major requirement in construction industry. For instance, degradation due to corrosion in concrete structures is actually it's a significant global issue, costing billions annually in repairs and maintenance. Western Europe alone spends like around I think 5 billion euro yearly on rust related damage, making repairs costly, time intensive. But this traditional approach of assessing the durability of concrete, just as we can see, is expensive, time consuming as well, and tedious. Just like I have on the screen here, these are the research. Sorry, the researches that have been conducted over the years in utilizing machine learning approach in determining concrete durability. So this first one is Zhang et al., which actually employed support vector machine to estimate the rate of chloride ingress in reinforced concrete. And we also have Nunes and Nedi, which actually use the gradient boosting regression tree to predict depth of carbonation. And this big picture here we have was actually conducted by Tafis in 2017, which actually employed this approach in determining the durability and service life of reinforced concrete. So all of this setup that we actually see, the aim is to actually determine the durability and service life of reinforced concrete. So let me next my slide.
It's visible.
All right, thank you. Okay, so this actually talks about um, image processing in concrete using machine learning approach. Non-destructive testing techniques are actually uh, indispensable tools for evaluating concrete structures without causing damage, which is a good one. But this method actually struggle to process effectively. Machine learning approach enhance this traditional way by analyzing the large data set to detect hidden defects, cracks, and other structural anomalies in concrete to actually save time, stress, and this is actually cheap to conduct. So from this, uh, Yokoyama in 2017 was able to conduct an assessment of cracks, just as we can see in concrete with CNN, and also Ryuta in 2018 employed artificial neural networks and support vector machines and support vector regression to evaluate concrete failure surface. At the end of the experiments, support vector regression produced the best result in comparison with the other two models. So that is for this. Let me next my slide.
It's visible.
All right, thank you. So here is how the traditional ways of concrete testing is being compared to machine learning approach. So when it comes to techniques used, the traditional way actually, just as we can see, it involves a physical and chemical test, destructive strength test, and the manual NDT image analysis. While the machine learning based approach involves predicting modeling. These AI driven image processing and oh sorry okay, so let me go to the next one. So as for time efficiency, the traditional way actually takes time to complete, just as we can see in days, and at times this process takes weeks, it takes months, but the machine learning approach is actually fast. And for material wastage, from the images I shared, the traditional ways actually involve physical samples, you know, to be destroyed. Why this is not so in the case of a machine learning approach. And in terms of accuracy and cost, the traditional way they're actually prone to errors and costly. Why reverse is the case when it comes to machine learning approach. And lastly, as for automation and scalability, the traditional ways actually requires manual input, and it depends on expert availability, while the machine learning approach is actually automated and easily scalable. Next slide.
It's visible.
All right, thank you. Thank you. Okay, so this talks about challenges and the future directions in um, the challenges of machine learning based concrete testing method. Sorry. Okay, yes. Okay, so the challenge is using this approach. The first one here, as you can see, is limited historical data. Just like the research I conducted myself, it was based on 1,030 data sets, which is not enough. That is too little. So this actually gives rise to reason why future research, to be focused on developing a large scale and a high quality concrete testing data set. And also model generalization difficulty. So machine learning models trained on specific data sets may actually struggle to generalize to new or diverse conditions such as different types of concrete or environmental factors or testing scenarios. Then also lack of standardized data collection. So the absence of standardized method for collecting and labeling data can lead to inconsistency in data sets, reducing the reliability and accuracy of machine learning models. And when it comes to high computational requirements, training and deploying advanced machine learning models, especially deep learning models, require significant computational resources, which can be costly and time consuming. And data security and privacy risk. So the use of sensitive or proprietary data in machine learning models actually raises concern about data security and privacy, particularly when sharing data across organizations or platforms. So for future directions in using this machine learning approach, well, the first one, okay, I think I've talked about the first one. So for the second one, which is improving model generation across diverse conditions. So enhancing the ability of this approach to generalize by incorporating diverse data sets and advanced techniques like transfer learning. So this will actually make them to be more reliable in real world applications. And for the third one, which is standardizing data collection and quality control, establishing standardized protocols for data collection, and quality control, we actually ensure consistency and reliability in dataset, leading to better model performance. And the fourth one, which is addressing high computational cost for machine learning models, optimizing algorithms and leveraging cloud computing or edge computing can reduce computational costs associated with training and deploying machine learning models. And the last one, which is enhancing data security and privacy in AI-driven concrete testing, implementing robust data encryption, securing secure sharing protocols, and privacy preserving techniques. Each, for instance, federated learning, we actually address concerns about data security and privacy. Uh, so, okay, okay, is that showing as well? Sorry, Kiran.
Visible, it's visible.
Is all right, thank you. So, as we have seen so far, that machine learning approach is actually revolutionizing the field of concrete testing by introducing innovative advancement that actually address the limitation of traditional method. So, this cutting edge technology are actually enabling faster, more cost-effective, and environmentally sustainable approaches to actually evaluating the quality and durability of concrete. As machine learning technology actually continues to actually advance, their potential to reshape this construction landscape becomes increasingly evident by integrating predictive modeling, artificial intelligence, and advanced data analytics. These methods are enhancing the safety and efficiency of concrete structures. And furthermore, the ability of this approach to process large data sets and identify hidden patterns actually ensures that concrete testing is not only more reliable but also scalable to meet the demands of modern infrastructure projects. And um, so all we can say in conclusion is that this approach, this machine learning approach, is not just transforming the way concrete is tested. It is paving the way for a new era of smart infrastructure development by addressing the challenges of traditional methods and unlocking new possibilities. And this approach are actually enhancing the safety, the efficiency and sustainability of concrete structures. As the construction industry continues to embrace these advancements, the future of concrete testing looks brighter with the promise of smarter, more resilient and environmentally friendly infrastructure. Okay, so this is the reference. And okay, so thank you all for your time and attention during my presentation. I hope you found the insight valuable, and I would like to open the floor for any question or comments you may have. Also, in case you love to stay connected or continue the conversation beyond the session, you can find me on LinkedIn by scanning the QR code which I have shared, or by searching for my name, Lanre Shittu.